Dear students, in this lecture I will continue with 0-1 integer programming. What I have done in this lecture, I have taken one problem on distribution, that is a common application supply chain management, where I have used 0-1 constraint for formulating the problem. The second topic which I am going to discuss is some of the modeling flexibility provided by 0-1 integer variables. Distribution system design, one of the important task of supply chain manager is how to design the distribution system. So, I have taken one sample problem. This problem is taken from the book Anderson et al. A company operates a plant. Already there is a company, they have one plant, say plant name is P5 with an annual capacity of 30,000 units. The product is shipped to regional distribution centers located in D1, D2, D3. There are 3 distribution centers and 1 plant. Because of this anticipated increase in demand, the company plans to increase the capacity by constructing a new plant in one or more of the following cities. So, the new cities which they are considering for constructing new plant is P1, P2, P3, P4. The proposed plant, there are 4 proposed plant, already one plant is there P5, but they are proposing 4 plant P1, P2, P3, P4. The annual fixed cost for this proposed plant is given and the annual capacity also given. And there are 3 distribution center D1, D2, D3 and their annual demand also given. Apart from this plant capacity and the demand, the shipping cost from these all 4 new plants and the existing plant also given. So, transportation cost is given. So, what is the meaning? In case if you are going to construct a plant at P1, if you are shipping the product from P1 to D1, the transportation cost is 5. Similarly, 2, 3. Okay. For example, P5 to D1 it is 8, P5 to D2 is 4, P5 to D3 is 3. So, this table represents transportation cost. So, now the problem which are there in the previous slide I brought into the network form. What this network form says? There are 4 proposed plant P1, P2, P3, P4. This plant is already existing. There are 3 demand point D1, D2, D3. Each proposed plant there is a capacity, all the values are in terms of 1000. Capacity is there 10, 20, 30, 40. This is an existing plant. So, the demand is 30, 20, 21. This number represents say P1 to D1, 5 represents unit transportation cost. P1 to D2 transportation cost is 2. P1 to D3 transportation cost is 3. So, likewise I have mentioned the transportation cost on the arc. Now, I am going to introduce the decision variables for the new plant. We have 4 plant. One is I am going to consider y1 equal to 1 if the plant is constructed at P1, y2 equal to 1 if a plant is constructed at P2, y3 equal to 1 if a plant is constructed at P3, y4 equal to 1 if the plant is constructed in P4. So, I may suggest 1 plant, 2 plant, 3 plant or 4 plant, maximum 4 plant I can suggest. The next element is the annual transportation cost. Okay. So, here I am going to introduce the decision variable xij. I represents the plant, j represents the demand. So, the unit shipped from thousands in terms of thousands from plant I to distribution j. So, 5x11 see this 5x11 2x12 plus 3x13. Similarly, 4x21 3x22 4x23. Likewise, I have written all the distribution cost along with the decision variables. For example, from P5, so P 8x51 plus 4x52 plus 3x53. So, this represents total transportation cost. Now, the annual fixed cost is given. So, 175y1, 300y2, 375y3 and 500 Y4. Now there are already we have discussed about the transportation cost. Now there is a fixed cost also. Now we will write the capacity constraint. For the plant 1, for the proposed plant 1, the capacity is 10. So what are the possible items which can leave from the plant 1? X11, X12, X13 less than or equal to 10 Y1. So the Y1 is the binary. So this constraint is applicable only if the plant 1 is selected. Say because we know Y1 is 1, 0. So this constraint is valid only if the plant Y1 is selected. So this I brought at the left hand side. This is minus 10 Y1. Similarly, the capacity of the plant 2, the proposed plant 2 is 20. So this will be X21 plus X22 plus X23 minus 20 Y2. For plant 3, capacity is 30. So X31 plus X3T plus X33 minus 30 Y3. For plant 4, X41 plus X42 plus X43 minus 40 Y4. And plant 5, it is already existing, you need not, there will not be any Y5 variables, but there will be a capacity, that capacity is maximum 30. So this is our capacity constraint. Now we will be writing on demand constraint. What is a demand constraint? You see D1, what are the possible way to reach D1? 1 1, 2 1, 3 1, 4 1, 5 1, that should be equal to 30. What are the possible way to reach D2? 1 2, D2, 3 2, 4 2, 5 2. Similarly for D3, what are the possible way? 1 3, 2 3, 3 3, 4 3, 5 3. These are the demand constraint. Now I have brought the complete model. In the complete model, first we will look at the objective function. Here the objective function is minimization type. What are the element is there? There is transportation cost is there. Up to this is a transportation cost. Then there is a fixed cost is there. You see that here fixed cost I am not subtracting because all the elements are cost. So I can directly minimize the cost. Then these are our capacity constraint. These are our demand constraint. So this problem I am going to solve with the help of solver. Now I am going to solve this distribution problem with the help of solver. I have written the decision variables in B3 to U3. Then the changing cells is from C4 to U4. Then the coefficient of objective function I have written. Then I have written capacity constraint and demand constraint. Here the value of Y1, Y2, Y3, Y4 is going to be the binary constraint. I will explain what kind of constraint I have considered. So data, solver. So this is minimization type. You see the constraint R4 to U4 is the binary constraint. Okay. All other constraints are as usual. Capacity constraint less than or equal to demand constraint is equal to type. When I solve it, so the value of objective function is 860. Now I will interpret this result into my presentation. The value of x42 is 20, x43 is 20, x51 is 30. So which plant is opened as per this solution? That only the plant 4 is getting selected. Out of we proposed 4 plant, out of 4 we are selecting only 1 plant to satisfy this current demand. So in this slide I have brought to our solution. The value of Y4 is 1, that means out of 4 only P4 is getting opened. So P4 demand is 40, capacity is 40. So from P4, so the D1 the demand requirement is 30. So the from P5 30 units are sent to satisfy. D2 demand is 20. Okay. So we know the P4 the plant capacity is 40. So 20 unit is distributed to D2 and the remaining 20 unit is distributed to D3. This basic model can be expanded to accommodate distribution system involving direct shipment from plant to warehouse, from plant to retail outlets and multiple products. How to consider that? Just we have to include a direct arc from the plant to demand center. Using the special properties of 0 1 variables, the model can also be expanded to accommodate a variety of configuration constraint on the plant location. For example, suppose in another problem, say site 1, site 2, a company might not want to locate plants in both site 1, site 2 because the cities are so close together. To prevent this result from happening, the following constraint can be added. How? If you write y1 plus y2 less than or equal to 1, what will happen? This constraint allow either y1 or y2 to equal to 1, but not both. So that is the benefit of 0 1 binary constraint. If we had written the constraint as an inequality, it would require that a plant be located either site 1 and site 2. Now the modeling flexibility provided by 0 1 integer variables. You remember we have solved this problem where we have to maximize the NPV. What are the data is given? Capital requirements and available capital. So P equal to 1 represents the plant expansion, W equal to 1 represents the warehouse expansion, M equal to 1 represents the new machinery, R equal to 1 represents new product research. Suppose that instead of one warehouse expansion project, the company actually has 3 warehouse expansion projects under consideration. So how to incorporate this kind of situation into our formulation? So one of the warehouse must be expanded because of increasing product demand, but new demand is not sufficient to make expansion of more than one warehouse necessary. So the following variable definitions and multiple choice constraint could be incorporated into the previous 0 1 integer linear programming model to reflect this situation. The first one we are going to consider multiple choice constraint. What is the meaning of multiple choice? Any one warehouse should be opened. For that purpose, we have to introduce W1 plus W2 plus W3 equal to 1. In this situation, if W1, W2 and W3 are allowed to assume only the value 0, 1, then one and only one of these projects will be selected from among these 3 choices whenever you write equal to sign. This is an example of multiple choice constraint. Now there may be a situation, mutually exclusive constraint. If the requirement that one warehouse must be expanded did not exist, the multiple choice constraint could be modified as follows. So if you write W1 plus W2 plus W3 is less than or equal to 1, so this modification allows for the case of no warehouse expansion, W1 plus W2 plus W3 equal to 0, but does not permit more than one warehouse to be expanded. Okay. We can have any one. So this is an example of, or it can be all 0. So this is an example of mutually exclusive constraint. Now there may be a situation k out of n alternative constraint. An extension of this notion of multiple choice constraint can be used to model situation in which k out of a set of n projects must be selected. Simply we can say a k out of n alternative constraint. Suppose that W1, W2, W3 and W4 and W5 represents 5 potential warehouse expansion projects, and that 2 of the 5 projects must be accepted. Then how to write this constraint? So this constraint that satisfy this new requirement, that is 2 of the 5 can be written W1 plus W2 plus W3 plus W4 plus W5 equal to 2. So that means out of the 5 only 2 will be selected. If no more than 2 of the projects are to be selected, we would use the following less than or equal to constraint. So, when you write the same constraint into less than or equal to type, what will happen? Maximum 2 is possible. The first one where there is equal to, you must have 2 warehouses. When you write less than or equal to, it should be maximum, it's 0 is possible, 1 is possible, 2. So, maximum we can go for 2 warehouse. Okay. Another way of how to write conditional and co-requisite constraints. Sometimes the acceptance of one project is conditional on the acceptance of another. For example, the company that warehouse expansion project was conditional on the plant expansion. So, what is happening? This type of projects, that is warehouse expansion and the plant expansion. So, generally in practical context, whenever there is a plant expansion, then only you should go for warehouse expansion. So, how to consider these constraints? That is, the management will not consider expanding the warehouse unless the plant is expanded. With P representing the plant expansion and W representing warehouse expansion, a conditional constraint could be introduced to enforce this requirement is W less than or equal to P. So, what it says that the warehouse expansion is possible only if you go for plant expansion. Here both P and W must be 0 or 1. So, whenever is P is 0, that is the plant expansion is taking place, if the plant expansion is not taking place, the W will be also forced to 0. If P equal to 1, okay, W is also allowed to be 1, but it can be 0 also. Thus, both the plant and the warehouse can be expanded. However, we note that the preceding constraint does not force the warehouse expansion project to be accepted if the plant expansion project is expected. So, there is a possibility W can become 0 when there is a plant expansion. Okay. But the warehouse expansion is possible only if you go for plant expansion. So, this type of constraint also can be incorporated. Then let us look at the co-requisite constraint. If the warehouse expansion project had to be accepted whenever there is a plant expansion project was or vice versa, we would say that P and W represented co-requisite constraint projects. How to write in the form of equation this co-requisite constraint? So, we simply write this co-requisite constraint W equal to P. So, this constraint forces P and W to take on the same value. If the P equal to 1, W also equal to 1. So, this is called the co-requisite constraint. If P equal to 0, W also 0. Now, we will go for some more flexibility in the binary variables. Like the following questions refer to the capital budgeting problem with the 6 projects represented by 0, 1. What are the 6 projects? X1, X2, X3, X4, X5 and X6. Now, write a constraint modeling a situation in which 2 of the projects 1, 3, 5 and 6 must be undertaken. So, how to write that one? When you say X1, X3, X5, X6 should be equal to 2. Okay. This is the first one. The second question is, write a constraint modeling a situation in which if the project 3 and 5 must be undertaken and they must be undertaken simultaneously. Okay. So, what you have to write? X3 equal to X5. So, otherwise X3 minus X5 equal to 0. What is the meaning simultaneously? When you go for X3, then X5 also should be there, then only you will get 0. If it is 0, this also should be 0. This is the another way. The next question is, write a constraint modeling a situation in which project 1 or 4 must be undertaken, but not both. So, when you write X1 plus X4 is equal to 1, okay, either whether we can go for 1 plus 0 equal to 1, otherwise 0 plus 1 equal to 1, but 1 plus 1 is not possible, because that will violate our constraint. The next question is, write a constraint modeling a situation where project 4 cannot be undertaken unless project 1 and 3 also undertaken. Now there is a conditional requirement. So when you write x4 less than or equal to x1, that means what? If you are going for x4, x1 must be taken. If you go for the second constraint, x4 less than or equal to x3, if you are going for x4, x3 also should be taken. In addition to the previous requirement what you have discussed in the previous slide, assume that when project 1 and 3 are undertaken, project 4 also must be undertaken. How to represent this one in the form of equation? So x4 less than or equal to x1. This is the constraint which we have discussed in the previous slide. Now what is that? The project 4 also must be undertaken. So how to represent this? x4 is greater than or equal to x1 plus x3 minus 1. So when you represent this way, what it says that when the project 1 and 3 are undertaken, project 4 also must be undertaken. See, if you are taking x1 equal to 1, x3 equal to 1, so 2 minus 1 1, then x4 also undertaken. The another important point in the integer programming is sensitivity analysis. See, sensitivity analysis often is more crucial for integer linear programming problem than the linear programming problem. A small change in one of the coefficients in the constraint can cause relatively large change in the value of optimal solution. Okay? So there won't be any proportional change. To understand why, consider the following integer programming model of a simple capital budgeting problem involving 4 projects and a budgetary constraint for a single time period. So objective function, the budgetary constraint is 100. So now what I am going to do, I am going to solve this problem with the help of Excel. Then I am going to increase this 1 unit on the right hand side. Let us see effect of this 1 unit increase on the right hand side of the constraint on our objective function. We will go to Excel. Now I am going to explain the concept of sensitivity analysis in the integer programming. So I have formulated the problem. You see the value of right hand side is 100. So go to solver. Look at this, the function is maximization problem. C4 to F4 is a binary. When I solve it, the value of my objective function is 170. Now I am going to see the concept of dual value. If I change the right hand side from 100 to 101, now if I resolve it, when I resolve it, you see that the value of objective function is 200. Just for 1 unit increase on the right hand side, the value of objective function is drastically increased. That is why you should be very careful while doing the sensitivity analysis. The sensitivity analysis in the integer programming means you have to resolve the problem. When the right hand side is 100, the value of objective function is 170. When I change the right hand side is 101, the value of objective function is 200. That is, one additional dollar in the budget would lead to $30 increase in the return. Surely management, when faced with such a situation, would increase the budget by $1 because there is a huge increase in the return. Because of the extreme sensitivity of the value of optimal solution to the constraint coefficients, practitioners usually recommend resolving the integer linear program several times with the slight variations in the coefficient of objective functions r and the right hand side value before attempting to choose the best solution for implementation. This is I brought the same problem. When it is 100, it was 170. When the right hand side is 101, there is a 200. In this lecture, I have explained the distribution problem with the 0 1 constraint. After that, I have explained various modeling flexibility provided by 0, 1 integer variables. Thank you very much.